Hi everyone. For today's lecture, we're going to continue studying triangles in hyperbolic space, and we're going to look at what are called two-thirds ideal triangles. So first let me tell you what I'm talking about. A triangle in hyperbolic space is of course given by three vertices connected by three geodesic segments. And I'm drawing these edges kind of curved inwards because we're on hyperbolic space. And of course, remember there's another way to visualize these, which is via our map to the upper half plane. And in that case, geodesics are given by half circles as well as vertical lines. And so under our map to the upper half plane, a triangle might look something like this. And we've also been talking about what are called ideal triangles because in hyperbolic space you can have lines which are not parallel but become asymptotic to each other as you go off in one direction infinitely far. And so you can replace vertices of a triangle with these asymptotic directions, and so you get something which feels like a triangle, except it doesn't actually have vertices because any two pair of geodesics end up not intersecting but just becoming closer and closer as you go off forever. So this is called an ideal triangle. And we've seen that in our map of the upper half plane, these can be formed like this. Oops. Or if I use all half circles as my geodesics, then it might look something like that. So that's an ideal triangle. And what I want to talk about next are what are called two-thirds ideal triangles. And the reason they're called two-thirds ideal triangles is two of the three vertices are ideal in the sense that they're just asymptotically approaching each other, not actually intersecting. So what I mean is I have one honest vertex with two geodesics coming off of it, but then the other two vertices are not vertices, they're given by the two geodesics becoming asymptotic. So something like that. This is a two-thirds ideal triangle, and so on the upper half plane it might look something like this, where I do actually have one vertex where two of the segments intersect, but I only have one vertex, and the other places where a vertex would be are asymptotic. Or maybe something like this if I'm using half circles. So that's what a two-thirds ideal triangle is. And so they have an angle associated to them. Maybe I call this theta. And that's the angle at the actual vertex. Okay. And these get mentioned in the book around page 93. So if you want to follow along, that's where it is. Now it turns out, for some kind of technical reasons, which we'll see later, that this interior angle theta is not what's most useful to talk about. It's actually more useful to talk about the exterior angle. And so if I extend this geodesic segment, I have this other angle alpha, which of course is just pi minus theta. That's the interesting one. So in this case, alpha's here, and in this case, alpha's here. So let's let I alpha be a two-thirds ideal triangle with exterior angle alpha. So that's the important thing to consider, not the interior angle. So as an exercise, you can do this using our isometries worksheet for the hyperbolic plane. Prove that all two-thirds ideal triangles with the same exterior angle alpha are congruent. So this is similar to the fact that all ideal triangles are congruent. Similarly, if you have two different two-thirds ideal triangles, like these two, if their angles at the vertices are the same, then they're congruent. So if the exterior angles are the same, then they're congruent, and this can be proven using what you know about the isometries of hyperbolic space via our upper half plane model. So what we're going to do today is calculate the area of one of these triangles. And since they're all congruent, if they have the same exterior angle, the area should only depend on that exterior angle. So our goal, we will calculate, I'll call it A rho of alpha, which is going to be the area of a two-thirds ideal triangle with exterior angle alpha on a given hyperbolic space. And remember, the hyperbolic plane, there's many depending on the radius. So this is on the hyperbolic plane of radius rho. Okay, so our goal is to find this number. A couple observations if we're trying to calculate this. So if I draw a two-thirds ideal triangle here, it really depends on the angle alpha essentially depends on where this geodesic L intersects this geodesic L prime. And notice that as I move L to the left, let's say, well, what happens to the angle alpha? Alpha gets smaller and smaller, right? If I move it over to here, this angle that I just drew in gray is smaller than the previous alpha. And so as I move to the left, alpha gets smaller. And the area of the ideal triangle, which we called A rho of alpha, gets smaller. The area of the ideal triangle is given by the area inside of this space here, right? And as I move L to the left, that area is shrinking. So we conclude that as alpha gets smaller, so does a row of alpha. And so that's fact one. Fact two is that the area varies continuously as I vary alpha. In other words, it's a continuous function of alpha. Why is that? Well, you can see that varying alpha just corresponds to moving this L to the left or to the right. And if I move L just a small amount, so if I change alpha by just a small amount, the area changes by a small amount. And intuitively, that's what it means to be continuous. If the input alpha changes by just a little, the output, a row of alpha, should also only change by a little. It shouldn't jump. So this is a continuous function. That's another way to say it. It's a continuous function of alpha. We can actually figure out some values already for this function. So alpha gets smaller and smaller as L goes to the left, and as this L approaches this third geodesic, L double prime, notice the area goes to 0. The space in here collapses completely, and that corresponds to alpha also going to 0, right? So if I draw it really, really close, here this alpha is really close to 0, and as L actually approaches L double prime, alpha is going to get to 0. And when that happens, the area between L and L double prime, of course, is 0, since they're the same line. So we know that a row of 0 is equal to 0. We know one other value as well, actually, which is we know what happens when L goes all the way to the edge of L double prime. So when I get to there. So I've moved L to the right to this gray line here. So alpha's increasing there, and it's going all the way up. It's getting closer and closer to 180 degrees, or to pi, right? And what happens when I reach that value? Well, what I have then is an ideal triangle, because this vertex here disappeared. It became asymptotic, and my 2/3 ideal triangle in the limit became an actual ideal triangle. And again, what that means for alpha is that alpha has gone all the way up to pi. And so as alpha approaches pi, our 2/3 ideal triangle, which I was calling, what did I call it? I alpha. Approaches, or looks more and more like, so turns into an actual ideal triangle. And so what that means, since a row of alpha is a continuous function of alpha, as alpha approaches pi, this area at pi, so a row of pi, has to equal the area of an ideal triangle, because that's what this 2/3 ideal triangle ends up looking like as alpha goes to pi. And we know what that area is. We calculated it in the last video. It's pi rho squared. So we kind of know the extreme values for this area function. We know it when alpha is 0 and we know it when alpha is pi. Our goal is to figure out what is it for all the in-between values. And the way we're going to do that is kind of roundabout. We're going to prove the following claim. Basically that a rho of alpha is a linear function of alpha. So if this is true, then what do we know? Well, if it's a linear function, then we know that it has a certain form. You know, linear functions of the form mx plus b. In this case, our input variable is alpha, so it looks like m alpha plus b for some choice of m and b, some constants. And then we want to figure out what those constants are, but we can use the values we already know. So a rho of 0, that's just equal to 0 times alpha plus b, which is just b, but we know that's 0. And also, so b is 0, and then we look at a rho of pi, that's equal to m times pi, but we know that's equal to the area of an ideal triangle, which is pi rho squared. And so m is equal to just rho squared. So once we have this claim proven, then that gives us that a rho of alpha is equal just to rho squared alpha. But let me write it in a better way. It's equal to alpha over pi times I rho where this is the area of an ideal triangle. So it's equal to the area of an ideal triangle times alpha over pi. Okay, so we need to prove the claim that this is a linear function. And the way we're going to do it is the following. We will show that it satisfies this property that linear functions have, that a rho of alpha plus a rho of beta is equal to a rho of alpha plus beta. So our goal is to prove this formula. And an exercise for some of you that know calculus is the following. If I have a continuous function, so if a rho of alpha is a continuous function which satisfies that property, then a rho of alpha is linear. So this is kind of a fun exercise. It involves using limits and what you know about continuous functions to prove this linearity. And actually, I believe that this actually just will show you automatically that a rho of alpha is equal to m times alpha with no b. So the goal for the rest of the lecture is going to be to show this. And I think I will pause right here so that you can digest what we've done, and in the next video, prove the blue.